very much. Well, I'm going to change course again. This has been a very wide-ranging session. Just like the previous talk, I'm talking about geometry related to the objects we're studying rather than statistical parameters. And in this case, it's about shape analysis. And the shape I'm going to talk about is not the usual shape analysis of similarity shape analysis, where we look for features of an object which are invariant under translation, rotation, and scaling, but instead about projective shape analysis, where we look at features invariant under a slightly larger group of transformations, that of taking a camera view of an object. And in particular, I'm going to take a scene of either collinear points in the plane or coplanar points in 3 dimensions and look at it in a film 1 dimension lower. And in order to visualize things for this talk, I'm going to emphasize the case of 4 collinear points so we can study it in more detail. We want to find the information in this scene that's invariant to the choice of the camera and the orientation of the film. And those features that don't depend on these pieces of information are called the projective shape. And in classical differential geometry, I guess it's called projective invariance. So the collection of all the projective invariants I'm going to call projective shape. Unfortunately, as it's usually formulated, projective invariants are not very suitable for quantitative statistical analysis. That is, there's no obvious metric to compare different sets of projective invariants. So the purpose of this talk is to try and develop a methodology that will facilitate metric comparisons. So as I said, I'm going to focus mainly on the case of k equals 4 collinear points, so they sit in m equals 1 dimension. And in this case, there's just one projective invariant, known as the cross ratio. And I'm going to look at the cross ratio and show why it's not particularly suitable for metric comparisons. So I'm going to give you a picture to show you what's going on. The 4 blue stars represent a scene in the real world of 4 collinear points. I'm going to take a picture of this with a camera. There's the focal point of my camera, and there's the film of the camera. And each of the green line represents a ray of light between the real world object and my focal point, and where it intersects the film is what you see on the film as a dot. Because I'm a mathematical photographer, I've put my film between the focal point and the real world object. Of course, in a real camera, the film is behind the focal point, but it doesn't make any difference to the mathematical development. And in order to see what's going on with the cross ratio, here's a picture I took of my back garden in England. And you can see down at the bottom of the garden is a flower bed, which is roughly a straight line. And I took this picture during daylight hours, and I came back at dusk and took another picture. My wife had bought some of these solar lanterns that absorb sunlight during the day and give off light at night. And she very carefully positioned them to be equally spaced in the flower bed. And I moved them so that the 2 right ones were closer together than the 2 left ones. And here I am standing at the house taking a picture down towards the back of the garden, and you can see that the 2 left lanterns look rather further apart than the 2 right lanterns. Then I went and stood on the bottom patio and took the picture back towards the house. So here I am standing at the bottom of the garden back towards the house, so the order of the lanterns is reversed. Of course, my camera angle is very different to what it was before. And you can see that the distance between the 2 left lanterns, which were the 2 right ones before, is now roughly the same as the distance between the other 2 lanterns. And so if you were just given these 2 pictures and asked, is the spacing of the lanterns the same in both camera views, my intuition is not good enough to say either yes or no. But if you calculate the cross ratio in this case, it turns out, let's see, did I calculate it? Yes, I got out my ruler on the image and measured all the distances and calculated the cross ratio, and they're virtually identical, 0.489 and 0.487. I don't usually get such close answers when I do numerical experiments, so I was quite lucky in this case. For those of you that haven't seen the cross ratio before, let me give a quick definition of it. If you have 4 real numbers, U1 out to U4, in this case representing coordinates of the blue stars in the real world, in some linear coordinate system, The cross ratio involves a ratio of products of differences between the u's. So in the numerator, I've paired up u1 and u2, and I've paired up u3 and u4, and in the denominator, I've paired them up differently. I've got u3 and u1, and u2 and u4. So I've taken the ratio of these products of differences, that's the cross ratio, and that's the feature that's invariant to my particular choice of camera view. And it can be shown that that's the one and only projective invariant in this situation. But which landmarks I call 1, 2, 3, 4 respectively is to some extent arbitrary. And you can ask what happens to the cross ratio if you were to relabel these landmarks. Of course, there are 24 permutations of the labelings of the landmarks, and it turns out that this gives rise to 6 possible versions of the cross ratio. And these 6 variants are given down here at the bottom of the slide. And if I were to originally restrict my cross ratio to take values between 0 and 1/2, these 6 transformations fill out the extended real line. So tau is between 0 and 1/2, 1 minus tau is between 1/2 and 1, and so on until you've eventually filled up the whole real line. Now, one of these transformations is 1 over tau. And it's this that helps make you realize why the cross ratio is not particularly suited to numerical metric comparisons between different projective shapes. Suppose I had 2 scenes that I was taking a picture of that happen to have very similar cross ratios. For example, 0.1 and 0.01. If you were looking on the tau scale, you would say, oh, those are very close together. The difference in the cross ratios is only 0.09, so they look very similar. But if you were to relabel the landmarks consistently in both scenes, you would replace the cross ratio by 1 over its value, and suddenly now the comparison becomes 10 minus 100, which is 90, and now it looks much, much larger. So in order to compare different cross ratios in a way that doesn't depend on the way you've labeled the landmarks, cross ratios themselves are not a particularly suitable way of representing this information. So what are we going to do? I'm going to look at a geometric solution and give an algebraic representation of it that will facilitate what's going on in this particular situation. The method does generalize to more landmarks and to higher dimensions, but I think today I'm going to focus mainly on this particular case. Let's suppose the landmarks are now labeled A, B, C, D in increasing order on the line. And what I want to do, first of all, is choose a preferred location for the focal point of my camera. And in order to do this, I'm going to draw 2 semicircles. One is going to have diameter A out to C, and the other is going to have diameter B out to D. And the 2 semicircles are going to intersect at a point, and I'm going to make that the focal point of my camera. So I'll show you a picture of that in a moment to see what's going on. And once I've got that focal point, I'm going to switch from using linear film, a straight line of film, to a circular film. And then the image of a landmark is now going to be a point, or in fact a pair of opposite points on the film, and that's now going to be my representation of my data on my film. Before I finish this, let's go look at the picture. So my points A, B, C, D are what I called 1, 2, 3, 4 before. They're in order. So what I do is draw a semicircle between A and C, a semicircle between B and D, and see where these semicircles intersect. I'm going to make that the focal point of my camera. And in order to do the second part of my analysis, I'm not going to use a linear film now anymore. I'm going to use a circular film. So the circle around my focal point O is my film, and each ray of light from the real-world object through the focal point, in fact, intersects the circle twice. I've not drawn both of the intersection points. So an image point of my film is really a pair of opposite points on the circle rather than just a single point. Now what can we see from this particular picture? Well, the angle AOC has to be a right angle because it's inscribed in a semicircle. Similarly, the angle BOD is a right angle. And so I've got 2 perpendicular frames of orthogonal vectors, and the angle between these 2 frames is what I'm going to use to describe my projective invariant. So the angles AOC and and BOD are right angles in this picture. And if I look at on AOB, so let me go back to the picture. If I look at this particular angle here, that's something that's very closely related to the cross ratio. Oops. I'm going to call that angle AOB an angle delta, say, and it turns out that's related to the cross ratio by the cross ratio is sine squared of that angle. Further, if I consider my 6 possible transformations of the cross ratio, it's related to the standard 6 trigonometric functions for representing angles, sine squared, cos squared, and so on. So that my angular representation gives me an alternative way of describing the same information that's in the cross ratio. But, whereas my original cross ratio took any value in the extended real line, my angle delta is going to range between an angle 0 and 90 degrees in this picture. So I've got a representation now that is more suitable for metric comparisons. So that's my way of choosing the focal point, and I'm going to use circular film. And once I've done this, my picture of my film image now looks like this picture here. The red X's are the points on my film, and although I've not drawn it, the red X and its opposite point are conveying the same information in this particular case. And the way I've rotated it, these two red X's are the same angle above and below the horizontal axis. The two top ones are the same angle to the left and right of the vertical axis. So I've collapsed my description of this situation down to a single angle delta. Why is this choice of focal point useful for metric comparisons? Well, now I'm going to do what I call algebraic calculations to show you what's going on. When you do projective geometry, it's much easier to work in homogeneous coordinates than the original Euclidean coordinates. So if my 4 points on the line are labeled U1 out to U4, I'm going to represent this information as a 4 by 2 matrix by adding a spare column of 1s. And I'm going to think of each row of this matrix as determined only up to an arbitrary multiplicative constant. So this now gives me a 4 by 2 matrix X containing the same information as my original 4 pieces for 4 numbers U1 out to U4. In general, if I have k landmarks in m dimensions, I'm going to get a k by m plus 1 matrix. And I usually write p is equal to m plus 1. So this construction generalizes to more landmarks and higher dimensions without any particular problem. And then it turns out that another way to describe projective shape is as an equivalence class of configurations under certain transformations. In particular, if I map my configuration X, in this case a 4 by 2 matrix, to dxb, it's going to represent the same projective shape. So here D is a diagonal 4-dimensional matrix representing the fact that in a film image you don't know how far away the real object is in the real world. All you can see is the image of that object on your film. And a 2 by 2 matrix B, which is non-singular. And that's going to mop up the effects of moving the focal point of the camera around. So projective shape can be described in terms of an equivalence class of configurations. And then if we want to do statistics, or in the language of similarity shape, if I want to do Procrustes analysis on shapes, what I'd like to do is choose a preferred element of this equivalence class to facilitate metric comparisons. So, what am I doing here? I'm recalling first of all the previous slide, X is equivalent to dxb, and I'm going to choose the diagonal matrix D and the non-singular matrix B so that 2 properties hold. First of all, I'm going to make the rows of X unit vectors. That corresponds to using the circular film I showed you on an earlier slide. And secondly, and perhaps more importantly, I'm going to make the columns of X orthonormal up to a constant factor, so that x dashed x is proportional to the 2-dimensional identity matrix. And that's going to make the points in my configuration as spread uniformly as possible around the circle in the sense of a moment of inertia matrix. Or if you'd like to think in terms of variances of 2-dimensional random variables, the sample variance of the matrix should So that's what I want to do, and then I'm going to justify why this is a useful thing to do. The choice of D. Since each row of x is only determined up to a multiplicative constant, I can scale it any way I like. And the usual way in homogeneous coordinates is to put the second column equal to 1. But I can make it a unit vector if I like, and that's actually more convenient for my purposes here. And then the choice for B is to make the data as uniformly spread around the circle as possible. Now, it's not immediately obvious that there's a solution to this problem. Is it possible to simultaneously choose matrices D and B so these properties hold? And the answer is yes, it is. And the solution, at least the only solution I'm aware of, is due to Dave Tyler, a statistician who developed a similar algorithm in the context of robust estimation of covariance matrices and multivariate analysis. There's no closed form solution for these matrices D and B in general. You've got to use an iterative algorithm, but it's one that tends to converge very quickly in practice.
It's unique, this guarantee.
It's unique up to rotation of the standardized configuration, up to a sign change about which side of the circle you're viewing your data point on, and I suppose you've got to choose a labeling of the landmarks. So
it's essentially unique.
It's essentially unique.
Yeah, right.
Why denote this standardized configuration? And it's unique up to multiplying each row of y by plus or minus 1, and multiplying the whole configuration by an orthogonal matrix in 2 dimensions. But it's going to give me data on the circle, on higher dimensions on the sphere, which is as uniformly spread around the sphere as possible. But I still got these remaining indeterminacies, which I want to deal with. How can I get rid of those? Well, I'm going to do something fairly simple-minded. In order to get rid of the effects of rotation, I'm going to take an inner product. So the inner product between 2 rows of y is invariant under an orthogonal transformation of the rows of y. And the indeterminacy in the sign of each row of y, I can just take absolute value of this inner product, and now these absolute inner products do not depend on those invariances. Or in other words, this matrix M I've defined here is a 4 by 4 matrix whose elements do not depend on any of the indeterminacies of my standardized configuration. So this is a projective invariant. And it's another way, in fact it's a crazy way, it's a 16-dimensional summary of the cross ratio, or of the information in the cross ratio. And there's also an inverse there that says from these standardized inner products, at least if P is equal to 2, that is, I've got collinear landmarks, I can go back and reconstruct the projective shape from this information, or in other words, reconstruct Y. So what does it look like in our case? Well, the picture I showed you before, the first 2 landmarks were equispaced above and below the horizontal axis, so that's C minus S and C plus S. The top 2 landmarks were equispaced around the vertical axis, so that's SC and S minus C, where little c and little s are the cosine and sine of half the angle delta. And this representation is unique up to, well, here I've labeled the landmarks in order from sort of smallest to largest. And if I would have a different ordering, I'd have to rearrange the rows of this matrix, up to the sine of each row of the matrix, and up to rotation and or reflection of the whole configuration matrix Y. And in this matrix, the cross ratio is related to this angle delta by one of these transformations we had in one of the earlier slides. So let's, well, that's that picture again. Why don't I put it up again? Just to remind you that the angle between these 2 blue lines is equal to delta. The angle between that blue line and that one is 90 degrees, so that they're orthogonal to one another, and the inner product is 0. And the angle between the first one and the fourth one is sort of complementary to the angle between the first and the second one. So when I construct this matrix of absolute inner products, well, first of all, I get some angle doubling going on. So I'm going to use a capital C and a capital S for the sine and cosine of the doubled angle. But you also see a structural zero in this matrix. So the first and third landmarks were orthogonal, so those have an inner product equal to 0. All the rows of this matrix in this simple case have the same information as one another. They all have elements 1, capital C, 0, and capital S. But the position of the 0 gives you information about the ordering of the landmarks. And that's going to be useful for our metric comparisons. So each row of the matrix, if I ignore the diagonal element, I've got 3 numbers, C, 0, and S, 3 numbers whose sum of squares is equal to 1. So that means I'm sitting on the sphere in 3 dimensions, but I've got a structural 0 on that sphere as well. So really sitting on the great circle, or really one of 3 possible great circles, depending on where that structural 0 is. So here's my picture of projective shape space with focal linear points represented as a spherical triangle. So at the top I've got the North Pole, I've got the Greenwich Meridian coming down to the equator, perhaps on the right hand side, another line of longitude coming down to the equator, 90 degrees apart, on the left hand side, and part of the equator down at the bottom of the picture. And as the cross ratio varies through the extended real line, I go through each of the various edges of the spherical triangle. So if the cross ratio runs from 0 to half, I go along half of one of the edges of this spherical triangle, half to 1 along another edge, another half edge of the spherical triangle, 1 to 2, 2 to infinity, minus infinity to minus 1, and minus 1 back to 0. Each of these describes a half edge of the spherical triangle. And whereas the numerical value of the cross ratio was not well suited for numerical comparisons, points on this spherical triangle are eminently suited for numerical comparisons. If I have 2 points on the same edge, I can use Euclidean or arc length distance between them. If I have 2 points on different edges, I can either use the arc length between them or the Euclidean or chordal distance between them. These are all plausible measures, and they're invariant to the labeling of the landmarks. So I've got myself a situation, or I suppose a family of possible distance measures that are eminently suitable now for quantitative comparisons. What have I said here? It's just saying in words what I've been saying a moment ago. The structural 0 in the absolute inner product matrix depends very much on the ordering of the landmarks and identifies which of the 3 edges of the spherical triangle I'm sitting on. At the vertices, this is where the angle delta either drops down to 0 or up to 90 degrees, and it's where pairs of vertices coincide. So if I go back to my, this picture here, if the angle delta drops to 0, the 2 nearly horizontal vertices become identified with one another, and the 2 vertical vertices become identified with one another. And that's really a rather interesting aspect of this interpretation of the cross ratio. If we go back to the original definition, there we go. Suppose landmark 1 and landmark 2 are equal to one another. The cross ratio is 0. The other 3 are all different. But in my standardized representation, if landmarks 1 and 2 are very close together, I'm also going to force 3 and 4 to be close together on my circular film, because there's only one angle delta representing the shape of that image on the circular film. So this slide is about why does the spherical triangle have corners? If I go back to my original definition of the cross ratio, now written in terms of ABCD rather than 1, 2, 3, 4, there's no strong reason for corners. If I hold 3 of the landmarks fixed, say A, C, and D, and let B vary, and provided B is never equal to D, so I stay away from the singularity in the denominator, the cross ratio is an infinitely differentiable function of B. And it doesn't feel like there should be any reason for a corner in the representation of projective shape space. But in my standardized representation, if B is being brought close to A, say, that forces my standardized version of D to be close to C, as I was just saying a moment ago. And that's the reason why these corners appear in the standardized representation that I've got. Okay, so here I've got several reasons why these corners appear. One is that the standardization of forces what appears to be a single pair coincidence to really be a double pair coincidence under standardization. That's A. B is that there are two distinct ways to move away from a singularity. So if the singularity is A equals B and C equals D, I can either move away in such a way that A is separated from C by B, or A is separated from D by B. There's two distinct ways, two of the edges, and they've got different separation properties. And there's also a third reason, which is that if I look at this standardized configuration Y, and look at the rank, not of Y itself, but a matrix related to Y, the related matrix has a rank which drops from 2 down to 1 at the corners. So there's a certain singularity going on. Okay, well, I've got about 1 more minute, and I'm really out of time. This is just the briefest of introductions to this subject, and the subject is really not mature yet. This is a lovely framework for thinking about projective geometry that seems to be a fresh approach to the subject, but there's still a lot of work to do in developing sensible statistical models in this framework. What a person called Steve Maybach, who's a very clever computer scientist, did a few years ago, was to say, suppose the 4 landmarks U1 to U4 have IID standard normal distributions, and work out what's the distribution of the cross ratio. And that also applies the distribution of this standardized version I've got here. And it turned out to be a hideous calculation where the density involved elliptic integrals at the end of the day. To such an extent that just by looking at the formula, you couldn't see the singularities in the density. It turns out that the density has a logarithmic singularity at each of the corners of the spherical triangle. So I suppose the message from that is that these distributions are really rather messy to work with if you go back to distributions on the original landmarks. And it's not clear to me that's the most promising approach to take. But I think I'll probably just leave it there, inspiring you to think for the next of these conferences about how to deal with such situations. Thank you.